Hello. In this video, I'll be explaining how to solve telescoping series problems. Before I cover that, I'm going to explain the very basics of a series, starting with what a series looks like and what it does. So this is a series, and it's composed of four different elements. The first is we have the Greek letter sigma in white, which is the symbol that depicts a series. Next, there's the index located beneath it in green, indicating what value the series begins with. In this case, it's n is equal to 1, therefore the series will start at 1 and it'll continue. There's the upper limit located above the sigma in orange, and it tells the series when to stop adding terms. Finally, there's a sub n, which acts as a function where terms are created. So now that we know what a series looks like, what does it do? Let's find the sum of this series. We can do this by first looking at the index, the upper limit, and a sub n. Let's first figure out what values we need to plug in into our a sub n. So since the index is 1, n will begin at 1, meaning that we'll replace our a sub n being n with 1. Bam. And I will add a marker n is equal to 1. Now we can move on and increase our n is equal to 1 to n is equal to 2, or increase our index. And when we do that, we're going to be adding another term, 2. And this is when n is equal to 2. And we're just going to keep doing this until we reach our upper limit, which is 5. And when we reach that upper limit 5, we can finally add everything together to get our sum, which is 15. Now, we could also change up our a sub n. Like, let's say, for example, our a sub n was n plus 1, and we had a series that went to 3, and n started at 0. We would first begin at the index where n would equal 0. So we plug in 0 for n, plus 1. 0 plus 1, that's equal to 1. And this is when n is equal to 0. Then we would add the next part. So now n is equal to 1. We plug in 1 for n. 1 plus 1, that's equal to 2. 2. And this is when n is equal to 1. And then we will just keep doing this until we once again reach our upper limit of when n is equal to 3. And in this case, 3 plus 3, 6 plus 4 is 10. And bam, that is the other sum. So that's kind of how a series works. Now, what about this series right here? Let's first look at its index. It starts at 1. And now let's look at the upper limit. Now, the upper limit isn't a finite number. It's actually infinity. How do we find the sum of something that goes to infinity? Let's try it out. We'll do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, and so on. Now, pretty quickly, you'll realize that you can't, because it's impossible. You can't just find the sum of infinity. It'd just be infinity. But if we use this method called telescoping, we can actually find the sum of series that go to infinity by using patterns. It's called the telescoping series. And it works by canceling terms out to where you're left with the first term or first few terms and with the last term. So let's see what that looks like. So this is a telescopic series. This series will run to infinity, and we're going to find the sum of this series. And to find the sum of this series, we're going to use 3 steps. The first step has already been done for us. We need to get a sub n and split it into the difference of 2 values. In this case, we have the difference between 2 fractions being 1 over n minus 1 over n plus 1. The next step is to apply partial sums and plug in values until you find a pattern known as the general solution. And we'll go into that next. And then the final step will be to take the limit of the general solution, which will give us the sum. So let's first try to find or try to use partial sums, and they're very, very simple. So the way I like to think of partial sums is by using another series and setting your n, by the way. So this s of 1, the sum of 1, series of 1, this 1 is going to be the upper limit, the sort of temporary fake upper limit. So we're going to plug in 1 for n. So we'll have 1, because 1 divided by 1 is 1, minus 1 divided by 1 plus 1, which is 2. Okay. Now, telescoping series, we need to find the pattern between our series, the terms, because we can only cancel things out if there's a pattern between them. And here there's only one term. There's no pattern. So we're gonna now go and set the upper limit to 2, and we're gonna just do this again. So the upper limit is 2, but we're still starting at an index of 1. So we just repeat 1 minus 1 half. This is the n is equal to 1 part. And now we're going to add this, because this is going to be another term, to the second term. To now, it's going to be our temporary upper limit to 2. So we plug in a 2 for n. We get 1 divided by 2 minus 1 divided by, what's 2 plus 1? 3. And already here we begin to see not a pattern, but things cancel out. We see that a negative 1 half will cancel out with a positive 1 half. And the trick with these is to kind of go, you usually want to go 4 terms in. So if we start at s of 1, we want to go to s of 4. So we're going to try out s sub 3 right now. 1 minus 1, didn't mean to write that. 1 minus 1 half plus 1 half minus 1 third plus 1 third minus 1 fourth. And then we're going to write the final s sub 4. 1 minus 1 half plus 1 minus 1 half, or plus 1 half, minus 1 third plus 1 third minus 1 fourth plus 1 fourth minus 1 fifth. And now if we take a step back, we can start to see a pattern, and things begin to cancel out a lot more. So first we're going to start off with the first term that we can cancel. We can cancel out a 1 half. Here we have a negative 1 half, we have a positive 1 half. We can cancel these two out. Same thing with the 1 third. We have a negative 1 third here, we get a positive 1 third here. We can cancel these out as well. And the same goes for the 4. We got a negative 1 fourth, positive 1 fourth right here. Cancel these out. Now, if you notice, we have two values remaining. We have a negative 1 fifth, and we have a positive 1. And these are going to be part of our general solution. So we'll denote this as s sub n. And no matter how many more values we add, if we were to do this to s sub 10, nothing is ever going to cancel out this 1, meaning that it's constant. It's going to stay the same. So we can make this 1 stay like that in our general solution. However, the last term in all of our series, all of our sums, it's always, if you notice, it's always 1 plus whatever we set the upper limit to. So we set the upper limit to 4 right here, but it's 5. It's always plus 1. Set the upper limit to 3 here, it's 4. Set the upper limit to 2, it's 3. So after noticing this pattern, we can see that the last term will always be negative as well. Negative 1 divided by n plus 1. N plus 1. And you can, I mean, if you really want to test it out, you can do an s sub 5, s sub 6, and just keep going on from there. Now, we finished the second step, and now all we have to do is move on to the third step, and we can finally find the sum. So we can write the limit as n approaches infinity of 1 minus 1 over n plus 1. And if you know your limit rules, you'll know that this fraction right here will be bottom heavy because the n is in the denominator. There's nothing up top. And that will leave us with a 1 as the answer. And that is the sum of this telescopic series. Okay, so now that we've solved one telescopic series, let's try another, a similar problem. Now, I want you guys to try this out on your own, but if you can't, just follow along. It's alright, so I'll give you guys a few seconds to pause and try it out on your own. Okay, so let's go through the steps again. The first step is we want to make sure that this telescopic series is split up and it has a difference. So again, we see that this is 1 divided by n plus 1, and it's in parentheses squared, minus 1 divided by n plus 2 in parentheses squared as well. So they're subtracting. So there is possible canceling out between terms. And now we're just going to use partial terms. And a tip that I want to tell you guys is don't fully multiply everything out. You see that we have squares in here. You don't want to multiply everything out because, or apply the squares because it's just going to make huge numbers and you don't need that to slow you down on a test or anything. So we're going to start off with 1 because this is at n is equal to 1. And the upper limit, we're going to, temporary upper limit is going to be set to 1. So we will have 1 divided by, we plug in 1 for n. 1 plus 1 is 2. And we will just have 2 squared minus 1 over, plug in 1 for n, we get 1 plus 2 is 3. 3 squared. And bam. All right, we're done. Barely fit it on there. So let's look at our S sub 4. Let's see if we can identify anything that can cancel out. So right off the bat, we can see that this 1/3 squared can cancel off with this other 1/3 squared because this is a negative and this is a positive. So these two can cancel. And let me do this in another color. So the 1/3 will cancel. The 1/4 will cancel as well because they're negative. The 1/5 will cancel. And you can notice that again, no matter how many terms we add, this 1/2 squared will never change. It's always going to stay the same. Nothing's going to cancel it out. So that's how we know in our general solution, we can leave that in there as a constant. And we can multiply it out now. We can do 2 squared, which is 4. And if we look at the last term, this is a 1/6 squared. And again, we can notice if we look back at all of these other terms, the last term is always going to be 2 higher than the limit, or the upper limit. So that means that we can copy it so we know that it's a 1, negative 1 divided by, and because it's plus 2, it's going to be n plus 2, and it's also going to be squared. And now if we were to take the limit of this, limit of as n approaches infinity minus 1 over n plus 2 squared. Once again, this will be bottom heavy. It'll turn to 0, and we are left with a 1/4 as the sum. Okay, so let's look at this problem. This problem is a little different than the ones we've done so far. The first thing you'll notice is that the index starts at 2. And you'll also see that instead of having 2 separate fractions with the difference between them, we just have 1. And that's a problem because now we don't have anything to cancel any other terms out, making it impossible to find the sum using partial sums. But we could fix that. All we need to do is separate this fraction into 2 different fractions. And we can do that by using partial fractions. So to do that, we're going to bring over this fraction, and we're going to factor its denominator. We're going to factor the n squared minus 1 into n minus 1 and n plus 1. And then we're going to set this equal to a divided by the smaller of the factor, n minus 1, And then we're going to add this to b, the larger of the n plus 1, or the larger factor. And so now we're going to get rid of this n minus 1 and n plus 1 in the denominator over here. And we can do that by multiplying by n minus 1 and n plus 1. Now what that's going to do is it's going to cancel out the n minus 1 and n plus 1 here underneath the 5. It's going to cancel out the n minus 1 on the a, and it's going to cancel out the n plus 1 on the under the b. And in turn, we're going to get an n plus 1 by the a and an n minus 1 by the b. So I'm going to write that out over here now. 5 is equal to a n plus 1 plus b n minus 1. And we're almost there. So now we just have to find what a and b equal. And that's really, really easy. All we have to do is make one of these two equal 0. And we can do that by letting n equal -1. If we let n equal -1, this a times n plus 1, if we make n -1, -1 plus 1 is equal to 0, that gets rid of the a. So we can do 5 is equal to 0 minus 2b, because if you have -1 minus 1 times b, you get -2b. And then from here we can solve for b, and we can get b is equal to 5 divided by -2. Now let's do the same for a. Let's let n equal 1. That's going to get rid of the b, and it's going to give us a 2a. So we'll have 5 is equal to 2a plus 0. Divide 2 on both sides. And then we get a is equal to 5/2. Great. But now what can we do with that? Well, we can restructure our fraction, and we can look at this a n minus 1 plus b n plus 1 before we multiplied everything. And we can fill in for our values. So we can put 5 divided by 2 into a, and we can put -5 divided by 2 into b. So now that we've rewritten our series, we have the newer series on the right here, and we have our older series over here. So actually, let me cross out the series, the old ones, so you don't get confused. So there we go. Now that we have the old series on the left, we don't need to worry about that anymore. And the new series on the right, we can now begin using our partial sums. And again, if we remember, our index starts at 2, meaning that we're going to start at 2 when we start doing our partial sums. So continue. 5 divided by 2 times, what's 2 minus 1? That's 1. So we get 1 minus 5 divided by 2 times 2 plus 1, that's 3. Awesome. Okay, so now we can begin canceling things out. So let's see what we can cancel out. We have a -5 divided by 2 times 3 here, and we also have a positive 5 divided by 2 times 3 over here. So we can cancel these two out. We have a -5 times 2 times 4 here. Actually, here, let's cut back here. We have a -5 divided by 2 times 4 here, and we have a positive 5 divided by 2 times 4 over here. You can cancel those two out. And I believe that's all we can cancel out right now. And this should be a 6 over here, not a 5. Okay. So now that we have that, we can begin assembling our general formula. We have 5 divided by 2 plus 5 divided by 4 minus, if we look over here, we have 5 divided by 2. And this 5 right here is the same value as this 5 over here. So that means that that just has to be n, doesn't need to be modified. So 2n. And this fraction over here, negative 5 divided by 2 times 6. This is 1 plus the 5. So we have 5 divided by 2 times n plus 1. Great. Now we can take the limit of this. And if we take the limit of this, the bottom heavy fractions will go to 0, and we'll be left with 5 divided by 2 plus 5 divided by 4. And if we add them up, we'll get 15 divided by 4. And that is the sum of this telescopic series. Okay, let's try out this problem. So this problem is similar to the other one. We have one solid fraction. We don't have the difference between two. And so we need to separate this fraction into two. So let's rearrange the series. First, let's rewrite the fraction over here. We're going to set it equal to a divided by the smaller factor, n, plus b divided by the larger factor, n plus 2. Next, we're going to multiply this whole thing, both sides, by n times n plus 2. And we are going to cancel out the denominator of the 2. We're going to cancel out the n, and we're going to cancel out the n plus 2, and we're going to be left with an n plus 2 over here and an n over here. Let's rewrite this problem. 2 is equal to a times n plus 2 plus b times n. Now we have to get a or b alone, and we can do this by letting n equals 0. It's going to let 2 is equal to, if we plug in a 0 for this n, we'll have 2. 2 times a is equal to 2a plus 0 because 0 times b is equal to 0. Divide 2 on both sides, and we are left with a is equal to 1. Let's do the same with b now. So let's let n equal negative 2. It's going to cancel out this over here. 2 is equal to 0 minus 2b. Divide negative 2 on both sides. And we're left with b is equal to negative 1. Okay, so now that we have that, we can rewrite our series. Okay, so now that we've rewritten our series, we can begin using partial sums. So let's start off with the series of 1. And we're going to plug in 1 for n. So 1 divided by 1 is equal to 1. Minus 1 divided by 1 plus 2, that's 3. Okay, great. So now that we've written out everything, we can begin to cancel out some terms. So we notice that we have a negative 1/3 here, and we have a positive 1/3 here, so we can cancel these two out. We have a negative 1/4 here, and we have a positive 1/4 here, and we can cancel those two out as well. So now all that we're left with is a constant 1 and a constant 1/2. And this negative 1/5 and this negative 1/6 will always be changing if you were to write more. So we'll have our S sub n, our general solution, with our constant 1 plus our second constant 1/2 minus 1 divided by this 5 is 1 more than this 4, meaning that it's a n plus 1. And this 6 is 2 more than our 4, meaning that it is an n plus 2. So now that we found our general solution, we can now take the limit of our S sub n. As n approaches infinity, 1 plus 1/2 minus 1 over n plus 1 minus 1 over n plus 2. We know that these fractions will go to 0. And we are left with 1 plus 1/2, which is also 3/2. Awesome. Okay, here's our next problem. So this problem, right off the bat, you can notice that we need to factor this as well. And so we can do this very simply, and we know that n squared plus 4n plus 3 can be factored into n plus 1 times n plus 3. So now that we've done that, we need to use partial fractions to split up these two so we can make a series that has a difference. So we can do this by first rewriting fraction down here, setting it equal to a divided by the smaller of the factors plus b divided by the larger of the factors. Next, we can multiply everything by n plus 1 times n plus 3. This will cancel out this over here, this, and this. And it will leave us with plus 3 up here and n plus 1 over here. Can rewrite this as 1 is equal to a times n plus 3 plus b times n plus 1 over here. Let's let n equal -1. We can get 1 is equal to 2a because we plug in a -1 to this n. -1 plus 3 is equal to 2. 2 times a is equal to 2a. Divide this by 2. Divide this by 2. This will also cancel out b. So we have -1 plus 1 gives us 0. Gives us 0. And we're left with a is equal to 1/2. Now let's let n equal -3. It's going to have 1 is equal to -3 plus 3 is equal to 0. A times 0 is equal to 0. Minus 2b, because if we plug in a -3 into n, -3 plus 1 is equal to -2. -2 times b is equal to -2b. We get a -2 over here. 2 over here. B is equal to -1/2. Okay, so now we can rewrite our series. Okay, so now that we've rewritten our series, we can now begin using partial sums again. So we plug in 1 for n. We'll get 1 divided by 2. 1 plus 1 is equal to 2. So 1 divided by 2 times 2. Minus 1 over 2. Plug in 1 for n. 1 plus 3 is 4. And that's s sub 1. Okay, so now that we've written out all of our partial sums, we can now begin canceling things out. So the first thing that we can see is that there is a -1 divided by 2 times 4, and there's a +1, so we can cancel these two out. There is also a -1 divided by 2 times 5, and there's a +1 divided by 2 times 5. We can cancel these two out as well. Okay, so now that we've done that, we can now write our general formula because we have two constants here, and we have the changing n plus 2 and an n plus 3 over here. So 1 divided by 4 plus 1 divided by 6 minus 1 divided by 2 times. We know that it's n plus 2 because this 6 is 2 above the 4 plus 2 minus 1 divided by 2 is n plus 3, and we know that it's n plus 3 because the 7 is 3 more than the 4. Finally, we can take the limit of this, and we can get 1/4 plus 1/6. We can simplify this so we can add them. We can get a 3 divided by 12 plus a 2 divided by. So we can get a 5 divided by 12. And that is the sum. of this series. Let's try out this problem. I'll give you guys a few seconds to pause this problem to try it out for yourselves. Okay, here we go. So the first thing that we need to do to solve this problem is to factor it. You can do this by knowing that this can factor into n plus 2 and n plus 4. Next, we need to turn this into two different fractions by using partial fractions. You can do this by setting this equal to a divided by the smaller factor, n plus 2, plus b divided by the larger factor, n plus 4. And then we multiply the whole thing by n plus 2 and n plus 4. From here, n plus 2 and n plus 4 will cancel, this n plus 2 and this n plus 4 will cancel, and we are going to be left with an n plus 4 up here and an n plus 2 up here. So we'll have a 6 is equal to a times n plus 4 plus a b times n plus 2 over here. Next, we need to get a or b alone, so let's let n equal -2. We plug in a -2 for n, we'll have 6 is equal to 2a plus 0, because -2 plus 2 is equal to 0, and if we have a -2 plus 4, we get a 2. Divide 2 on both sides, and we are left with a is equal to 3. Now let's do this for b. Let's let n equal -4. 6 is equal to 0, because if you plug in a -4 into n, -4 plus 4 is equal to 0. 0 times a is equal to 0. And then we'll have a -2b over here, because -4 plus 2 is equal to -2. -2 times b is equal to -2, 2b. Divide this on both sides, and now we're left with a b is equal to -3. Epic. So now we can rewrite our series. So now that we've rewritten the series, we can move on to partial sums. But before we do that, I want to show you a neat little trick we can do with series. So I've been avoiding this up until now because the numbers haven't been too large, but this can help you save time. So notice how we have a shared 3 in both of these fractions. Well, we can actually just pull out the 3 and bring it outside on the series, leaving us with a 1 divided by n plus 2 minus 1 by n plus 4. And then we can just reapply this when we have our general solution. And this will just help us write the partial sums a lot quicker. So let's do that. S sub 1, plug in a 1 for n, we get 1 divided by 3. Plug in 1 for n over here, we get -1 divided by 5. Okay. So now that I've rewritten everything out, we can begin to cancel things out. So we notice we have a -1/5 here, and we have a +1/5 there, so we can cancel these two. We have a -1/6 here, and we have a +1/6 here, and we can cancel those two out. So now that we've done that, we have our two constants, 1/3 and 1/4, and then we have the numbers that will change constantly. So we can write our general solution S sub n. We know that we have a 1/3 plus a 1/4 minus a 1 over n plus 3. We know that it's n plus 3 because this 7 is 3 above the upper limit. And we know that this 8 is 4 above the 4, so that means that it's n plus 4. And then from here, we can distribute out the 3 that we took out from the series. So multiply this all by 3, and we'll just get 1 plus 3/4 minus 3 plus 3 minus 3 divided by n plus 4. And this is our general solution. Now we can take the limit of our general solution, these will go to 0 because they're bottom heavy. And then we're left with 1 plus 3/4, which we can get 4 divided by 4 plus 3 divided by 4. And that will leave us with 7/4. And that is the sum of this series. Awesome. Okay, so here's our last problem. So right off the bat, you'll notice that this problem is a little bit different. Its index starts at 4, but more prominently is that you'll notice that the n plus 4 and the n plus 3, the smaller of which is negative. And usually it's the other way around. Usually the larger, in this case it'd be the n plus 4, would normally be negative. And that's going to change our answer. Before we get into that, I want to give you guys the opportunity to pause and try this problem on your own, because you should know everything you need to know to solve this on your own. But if you want to follow along, it's all right too, so I'll give you a few seconds. All right, great. So going back to our steps, this problem's already has a difference. We don't need to do partial fractions or anything, so we're actually ready to do partial sums. But real quick, before we even do partial sums, we can simplify this series by bringing out the 3 and making it a little bit easier for when we do partial sums. So we'll bring out the 3, and we'll be left with a 1 divided by n plus 4 squared minus a 1 divided by n plus 3 squared. Okay, now we can commence partial sums. And we're going to start at s sub 4, not s sub 1, because the index is 4. And now we're going to plug in 4 anytime we have 1, or n. So we have 1 divided by 4 plus 4, which is 8. It's going to give us 8 squared minus 1 divided by 4 plus 3, which is 7 squared. Okay, so now that we finish writing out our last partial sum, we can begin canceling things out. So first thing that we can cancel is we can cancel out the 1 divided by 8 squared with this negative 1 divided by 8 squared. We can also cancel out this 1 divided by 9 squared with this negative 1 divided by 9 squared. And we can also cancel out this 1 divided by 10 squared with this negative 1 over 10 squared in the corner over here. So now we're left with a general solution. We have our constant right over here, which is 7 squared, which actually let's just factor that out and simplify it. So negative 1 divided by 49. And then we also have our variable, this term, which will always be constantly changing. This term is 11, and 11 is 4 more than 7, meaning that we will add n plus 4 to it, and we can square this. And that's our general solution, except that we need to multiply this now by 3, because we took out a 3 before, which will leave us with a negative 3 divided by 49 plus a 3 divided by n plus 4 squared. Finally, we can take the limit of this, which will get us negative 49 plus 3 by n plus 4 squared. This goes to 0 because it's bottom heavy, and this leaves us with negative 3 divided by 49 as our sum. And the reason why I said this problem would be a little bit different, because the larger number, the larger n plus 4 would be positive and the smaller one would be negative, is because our answer is now going to be negative because of that. And that's that. Okay, so before I end this video, I just want to say a few things. First thing is, thanks for watching this video. The whole reason why I'm doing this video, or this channel, is because I want to help people out. Calculus can be a very difficult subject to learn, and it takes a lot of time. It really does. And so, even if you're doing bad and you don't think you're doing well, don't worry. I mean, the best way to learn calculus is through repetition, just practicing problems over and over, looking at other YouTube videos, stuff like that. Um, and I plan on making more YouTube videos. Geometric sum video, probably gonna happen after this. Divergence tests, limit comparison test, P series tests, everything about series. Then I'm gonna go back to limits, derivatives, and integrals. And I want to try to follow the similar structure that I have in going on to this video, where I have a bunch of different problems, and I want to have, a few so you get the basic idea on how to solve problems, a few that are harder, and then a few that might show up on quizzes, tests, or exams. And if you notice that I make a mistake or there's something wrong in one of my videos, please point it out. I definitely want to fix that. I don't want to spread any misinformation and mess up people's understanding on this. So, yeah. Anyway, thanks again for watching this video, and I'll see you later.